Welcome back everybody for a new session of the colloquium. It's my pleasure to introduce today's speaker, Sam Payne from University of Austin. Sam got his PhD at Ann Arbor at the University of Michigan. After that, he was a Clay Research Fellow at Stanford, and then he was a professor at Yale, and now he's currently in Austin, Texas. He has won several awards, such that Simon's Fellowship, and he is a fellow of the MS, and is currently visiting Montreal thanks to a Simon Fellowship. And today he's going to talk about point counting and my phone crashed, point counting, modulo P, and the cohomology of the moduli space of curves or something like that. Sorry.
Yeah, that sounds fine. Thank you, Giovanni. It's okay, and so this is colloquium, so I'm going to start from the very beginning, and apologies to experts. So the general area is algebraic geometry, and so we're going to study solutions of systems of polynomial equations, such as the solutions to one equation, and the equation will be a polynomial. And we could take coefficients in various rings or fields, but let's start with the example of integer coefficients. If we have a polynomial with integer coefficients, we can look at the solutions in different fields. We could look at rational solutions, integer solutions. We could look at complex solutions and study the topology, and we could look at solutions over a finite field. And here in particular, we could count the solutions. So just for notation, I'll write number of x to be the number of solutions of x over the finite field fq when q is fixed. And so we should start with some examples. So we could take an affine linear equation in two variables, and for any value of x that we plug in, there will be exactly one value of y that solves the equation. So here's our x, and so we have exactly q solutions. And so this is right. So this is the affine line, and so people write a1. We could just as well take the affine plane. So y equals a1 x1 plus a2 x2 plus b. And so then we would have some affine line. But again, if we plug in any x1, any x2, then there's a unique y that solves the equation. And the number of points is q squared. Okay, so we could do affine n space similarly, and there will be q to the n points. So now let's do another example. So here we have some algebraic varieties are moduli spaces. So we could take P1, which is a good example of a moduli space. So it's the space of lines through the origin in the affine plane. And so if we have the affine plane and we have our origin, we could choose one affine line, and then almost every line through the origin will meet this affine line at one. And so we have an A1 worth of lines, and then there's exactly one line that doesn't meet that, and that's the line parallel. And so we have a disjoint union of A1 and A0, and so point counts will certainly be additive for disjoint unions. The number of points on P1 is q plus 1. Okay, and we could do this similarly for the number of points in the projective plane. So lines through the origin in 3 space, and we'll have an A2 of lines, and then we have a plane parallel to that affine plane. And so the remaining lines are the lines through the origin in this plane, which would be P1. So the number of points in P2 is q squared plus the number of points in P1, which is q plus 1. And we could play this game differently. So if we have points in P2, well, these are lines, and one way to determine a line is to choose a non-zero point, and then the orbits of points under the action of the multiplicative group GM, those would be the points of projective space. So we have GM, which is A1 minus the origin, and so the number of points there is q minus 1. And the projective space is the affine space of dimension 1 higher minus the origin divided by the action of the multiplicative group. And the point counts behave well. So here we would have that the number of points on Pn, well, this is the number of points in affine space minus the origin. So that would be q to the n plus 1 divided by q minus 1, which is indeed 1 plus q squared up to q to the n. So that's first example of point counting. And all the examples that I've given you so far, the number of points was a polynomial in the size of the finite field. So polynomial in Q. And there are more such examples. So we could take, instead of the space of lines in AN, we could take K-planes in AN, and the Grassmannian has the Schubert cells. So it's a disjoint union of affine spaces, and so that gives you a polynomial point count. There's the space of flags, so the space of lines contained in planes contained in 3 spaces, and so on. So this has analogous cells, the Bruhat cells, and that gives it a polynomial point count. There's torque varieties. So instead of being tiled or paved by affine spaces, torque varieties are tiled or paved by products of copies of GM. And so polynomial point count behaves well with respect to product complements, disjoint unions, and so one arrives at Tataro's linear varieties. So all spaces that are inductively built out of affine space by products, complements, disjoint unions. So all of those have polynomial point count. So let me give an example that doesn't seem to immediately fit into that. So we could take the affine plane, and then we could quotient by the action of z mod 2z. So we're going to quotient by an involution. And so xy is related to minus y minus x. Okay, and so now we want to count points on this space X. And and now the story is going to depend on so the way I tell the story will depend on the parity of Q. So let's assume that Q is odd. And so now we want to count points on X. So one type of point on X would be in orbit of points on A2 over FQ. And so orbits of XY in A2. Okay, and so there are 2 different types of orbits. There are orbits of size 1 and orbits of size 2. And so you can check that there are Q orbits of size 1 and Q squared. So the other orbits, there would be Q squared minus Q divided by 2 because the orbits have size 2. So these are orbits of size 2. And so far we have Q squared plus Q over 2 points, but those are not all of the points because we also have pairs of points both defined over FQ squared that form an orbit under the action of this involution. And so you could look at solutions to x to the q equals minus y and minus y to the q equals x. And so those solutions will live over fq squared. And there will be, you can go ahead and check q squared minus q over 2 of them. And so then you add these up, you squared. And so it is the same as the number of points on A2, but there's no natural bijection between the 2.
What is the polynomial on the left? Is that x to the q?
this should be x. These are x to the q equals minus y, and why did I write that? Now I've confused myself. So we want points over fq squared. So what I want, so what's happening here? Okay, so what's happening here is, so I want a subset of A2 over FQ bar, Frobenius, and forms an orbit under this action. And so that means that x to the q has to be equal to either x, but if it's equal to x, then x was defined over FQ. So if it's over FQ squared, but not over FQ, then x to the q had better be minus y. And y to the q should be minus x. And so those are the equations that we're writing down. And so there's q squared minus q possibilities for the choice of x in fq squared minus fq. And those fall into orbits of size 2. So we get q squared minus q over 2. Okay. And so then at the end of the day, we get q squared. So here's another example of variety with polynomial point count. That is not, at least not obviously, of the form of the other ones that we've looked at so far. So that was what I wanted to show. And then, of course, as Prospero said, there is more on heaven and earth. So not all varieties have polynomial point count, and so let's remind ourselves of that. So this would be a non-example for polynomial point count. So we could take a slightly more interesting equation that's familiar to many of you. So y squared equals x cubed plus ax plus b. So a truss cubic, and so then we can write down the discriminant minus 16 27 b squared, and we should assume that the discriminant is relatively prime to the size of our field, so that the geometry is nice. So this is our space X, and the number of points on X heuristically should be about Q. So why is that? Well, we plug in a value for X, and we have, well, Q different choices for a value for X. And 50-50 shot. Maybe this is a square and maybe it's not. And if it's, then there are two values for y. Okay, and then the other possibility is that it's 0, but then there's one value for y. So in all of the cases, the sort of expected number of solutions for an input x is about 1. And so that's the heuristic. And then the theorem that I think goes back to maybe Hasse in the 1930s, conjectured by Emil Artin, is that the number of points on X is Q plus some error term AQ, and the size of the error term is less than or equal to 2 square root Q. So the heuristic is pretty good, and we have a very specific bound on how good okay, and then there's what one can say about these error terms. So and many others says that, so if we look at AQ divided by 2 square root Q, and we look at how that's distributed as Q grows. So this satisfies Sato-Tate. So that means that, so the probability density, so this is some number between -1 and 1, and so it's equal to cos for some at some angle theta. And the probability density at cos theta is proportional to sine squared theta d theta. So this is some very specific distribution for how the error terms go. So there's quite a lot going on to be said there. And moreover, if we fix x and vary q, then we get all these different numbers aq. And these are coefficients in the q expansion of a modular form. And so this is work of Wiles and Roy, Conrad, Diamond, and Taylor. And so this is, as conjectured by Shimura, Taniyama, and Wei. And so this is what leads to the proof of Fermat's last theorem. So I am going to focus on spaces with polynomial point count, but I don't want to give you the impression that that is the only interesting part of the story. So when polynomial point count fails, the failure has dramatic and wonderful structure that is worthy of much attention and investigation. And you might say, well, okay, so these are the curves of genus 1. So when we went from rational curves to curves of genus 1, we went from polynomial point count to non-polynomial point count. And that was the transition from Kodaira dimension minus infinity to Kodaira dimension 0. And there's an analogous bound. So if we went to curves of genus G, we would have Q plus an error of size less than or equal to 2G square root Q. So that was Wei's bound. And so you might say, oh, so this is going to be wrapped up in Kodaira dimension by rational geometry of varieties. And it sure would be to think so. But there are surfaces of general type that have polynomial point count, smooth projective rational threefolds that have non-polynomial point count. So polynomial versus non-polynomial point count is some measure of the complexity of the variety, but it's not a measure of the geometric complexity. It's really a measure of the cohomological complexity. And so I'll try to explain some of that as we go. Okay. And so I am going to want to talk about point counts on moduli spaces. And moduli spaces typically not varieties. They tend to be stacks. And so I should tell you a few words about point counting on stacks. And so let's start with, and you should think of stacks if you're topologically minded as being orbitals. So all the stacks that show up will be Deligne-Mumford, so algebraic orbifolds. And so the simplest one we could take would be to take a finite group, and then we'll take the classifying space of that group, which is the quotient of a point by the group. And well, then we want to understand what does it mean to have a point on the classifying space over FQ. And so that would be, well, the space or the set of principal G bundles on a point defined over FQ. So principal G bundles on spec FQ. And one thing that one learns when counting objects with automorphisms, based on experience, it is always the correct thing to do to count these objects with multiplicity inversely proportional to the size of the automorphism group. And so, note each principal G bundle has automorphism group G. So G acts simply transitively on the bundle. And so then, however one defines point counting on stacks, so this should be the set of points, so morphisms from spec FQ to X. So sum over all points, and then divide by the size of the automorphism group. So if we're counting points on BG, we're just going to count the number of principal G bundles and then divide by the size of G, because they all happen to have the automorphism group. If on a more complicated stack, there might be different points that have different automorphism groups of different sizes. So what does it mean to give a okay, so here we have our principal G bundles. So these would correspond to morphisms from the fundamental group. And here we should take the étale fundamental group into G. And now the étale fundamental group of of a point is the Galois group. And so these are maps from Z hat to G, continuous maps. And Z hat is the completion of the cyclic group Z. And so there's one map for each place that the procyclic generator can go. So the sum of this is G. And so we've done a long computation to decide that if you take a point and you quotient by a finite group, you get one point. Polynomial point count. So that's nice. Yeah. Oh, now I just erased another example, but now we've seen two examples of spaces with polynomial point count that we quotiented by a finite group, and we got polynomial point count. Okay, so that's interesting. So now let's say that we have an algebraic orbifold defined with integer coefficients, and then okay, so then we have this definition of the number of points on X. So we count morphisms from a point into X, and we count those morphisms with multiplicity 1 over the size of the automorphism group of the morphism. And so this is from Kai Barron's. So the point count so defined satisfies a number of nice properties. So first of all, it's additive for disjoint union. So if we have, so if we write our stack as a disjoint union, then the number of points on X is the sum of the number of points on the pieces. Here's another good one. So if X is a quotient of an algebraic variety by a group, but not just any group, we want G to be connected linear algebraic group, so like GLN, then the number of points on X is the number of points on the original variety divided by the number of points in the group. So that's another good property. So let's do one more property. In great generality, algebraic orbifolds have moduli spaces. So you can forget the orbifold structure and you'll get something defined by equations. It behaves just the way you would imagine that that if you were working over the complex numbers, then the coarse moduli space would topologically be the topological quotient by the group action. So if X has a coarse moduli space X, then stack is equal to the number of points on the coarse moduli space. Okay, so the way we defined point counting on stacks, it looks like you might get rational numbers out because we were dividing by sizes of automorphism groups. But those point counts are equal to the point counts on the coarse moduli spaces, so they are integers. So these seemingly miraculous things where integers come out are not miracles. They are just sort of part of the structure of the theory. Okay. Maybe now we're getting to the point where we can talk about the relations to cohomology. And here, the thing to keep in mind is that when we work on an algebraic variety geometrically, so if we're working over a field like the rationals or FQ, then our polynomial equations might not have any solutions. So the geometric space that we think about is the solutions over the algebraic closure. And then the solution, so if we're working over the algebraic closure for FQ, then the solutions that are defined over FQ are exactly the solutions over FQ bar that are invariant under the action of Frobenius. So we have this space that we think of as being like a manifold. We have Frobenius acting, and when we count points over FQ, it's like counting fixed points for the action of this endomorphism. And so I should remind you of a sort of early theorem in topology going back to Lefschetz. And okay, so there are much more general versions of this, but let's look at an easy version. So if X is smooth, compact, manifold, and phi is an endomorphism with points and orientation preserving, then, well, if we count those non-degenerate fixed points, this is the sum over all I times the trace of phi upper star on HI XQ. So the singular cohomology. Okay, so counting fixed points for an endomorphism in a nice situation means taking the graded trace of the pullback on cohomology. And I said compact, so you could cohomology or compactly supported cohomology because they're the same. And so on algebraic varieties, we don't, if we're working over FQ, we don't have this singular cohomology to work with, but we have something almost as good. Aaron's version, the Lefschetz formula. And so that XB, so a Mumford stack over finite field FQ. Then the number of points as defined over there is equal to the sum over I minus I, the trace of acting on the compactly supported étale cohomology of X with coefficients in QL for any L prime to Q. Okay, so this is saying that Frobenius acts on the L-adic étale cohomology as if it were an endomorphism acting on a nice topological space in a nice orientation preserving way. And that we can count fixed points accordingly. Okay. And so now
so if you were to replace X with its course moduli space, then I guess you could you apply the same theorem? You couldn't, because it wouldn't be smooth.
You can. So smoothness was sort of a red herring there. I wanted to say orientation preserving, and okay. But yes, so the L-adic étale cohomology of a Deligne-Mumford stack with QL coefficients is canonically isomorphic to that of its course moduli space. And so then you could look at the, yeah. So yes, all of this will be true. You could go course space, you can go stack, as you prefer, depending on what's convenient in any given situation. Okay. Let's say we have G, a finite group. So this is a situation that we've seen. We have a finite group acting on affine space. Well, the compactly supported cohomology of affine space has rank 1 in degree n. The cohomology, so H star of A is just freely generated by the fundamental class. And the eigenvalue of Frobenius acting on that fundamental class is q to the n by the trace formula, right? We know an has q to the n points. So one space, so the eigenvalue has to be q to the n. And then if we have a finite group acting, it has to preserve the fundamental class. So and then the right. So if we take group, well, that's the G invariant part of the cohomology of the space we started with. Well, that one-dimensional space has got to be, G invariant. And so, yeah, so then this means that the number of points on AN quotiented by any finite group is q to the n. And it's q to the n a way that does not give you a bijection with the points of an. So that calculation we did where there were 3 different cases and there were denominators and everything added up to q squared, that's one very simple example of just a general phenomenon that take affine space and quotient by a finite group, and you get something with q to the n points. There's automorphisms. It's not endomorphisms. So yeah. And so now so what should I say now? So now I should remind you that we actually know quite a lot about how Frobenius acts on L-Lattice cohomology of algebraic varieties and Deligne-Mumford stacks. So this is theorem of Deligne. So let X be smooth and proper. Then, so we could look at the eigenvalues of Frobenius acting on the L-Lattice cohomology of this proper space. So these are our algebraic integers of size q to the I over 2. So for any embedding, for any identification of QL bar with the complex numbers. So this is Deligne's proof of the Riemann hypothesis. And again, this is a statement that's really just saying that Frobenius is acting like an endomorphism of a nice orientable manifold. So here's a theorem of Serre that predates this theorem of Deligne. So a wonderful, right, so this was a letter to André Weil that was published in the Annals. The paper starts, Mon cher André. And okay, and so here's what, so Serre wanted to explain to André Weil the meaning of the Weil conjectures. And so here it is. So let X be smooth, projected over the complex numbers, and D a hyperplane section. So an simple class. And so then we could take an endomorphism of this smooth projective variety such that the pullback is Q times the class of D. So it acts on the hyperplane class by rescaling. And so then Serre explains using linear algebra and Hodge theory that the eigenvalues of F upper star on HI X have size Q to the I over 2. Okay, so once again, the moral is that Frobenius acts on L-Lattice cohomology of something over a finite field. A endomorphism would act on the cohomology of a nice complex manifold. And here we could, you can also, so if lambda 1 through lambda r are the eigenvalues on HI, then Q to the n over lambda 1, Q to the n over lambda r, these are the eigenvalues on H2n minus I. Okay, so that's using Poincare duality. And this leads to the functional equation for the zeta function. Okay, and so here, so a corollary So say we have x smooth, proper over the integers, then the point count is a polynomial in Q. So this is if and only if hi is either 0 if I is odd, and Q to the I over 2 eigenspace if I is even. So polynomial point count is just the same as all eigenvalues being Q to the I over 2. It turns out also to be equivalent to that on the complex fiber, the Hodge structure is pure PP. So okay, but that's going in a different direction. This is a corollary of Deligne. Yeah. So Serre's theorem is motivation for Deligne's theorem. So right, yeah. So Serre's theorem is, in some sense, the philosophy that explains why one should expect phase conjectures to be true, or what.
This is a very nice question. Look at this corollary. You might say naively, why not look for varieties where the point count is a polynomial in square root of 2 rather than 2?
You could do that.
Yeah, you could conceive of that, right? And then is it obvious that they're the same as your definition?
No, so that can't happen, right? So that can't happen because and the reason here is that we defined it over Z, and so this means Q is allowed to vary, and in particular, Q can be the square of a prime. And okay, so let me not go through the details, but yeah, that does not happen. Okay. I feel like I'm about to make an abrupt transition, but colloquiums have abrupt transitions, right? So we start off at the beginning, and then we get to things that all of this stuff that I'm saying. This is Serre's paper is from the 1950s. Deligne is from the early 70s, right? So we're talking about 50 plus years ago. So now we want to come closer to the present day. So this is a few years ago. Okay, so what, right? So how do I want to set this up? So again, we want to be in situation smooth and proper over the integers. And so what does this do? So this means that we're going to have representations of Galois that have good reduction at every prime p. And then we should be able to package the eigenvalues of all of those, all of the Frobenius at all q, and build an L function. And the assumption here, which is widely believed to be true, is so we assume that the L function attached to all F's of the Galois group that appear in the okay. So if you believe a suitable form of the Tate conjecture, then you believe that the cohomology is semi-simple. But until then, we'll take the semi-simplification of cohomology, and we want to assume that these have analytic continuation with the functional equation of the expected form, so which involves the conductor, which is a positive integer divisible exactly by the primes of bad reduction, or the primes, oh yeah, primes not of good reduction. And so here the conductor should be 1. So all the representations appearing here have conductor 1, and then that gives some control over what the analytic properties of these L functions could be. And so then using Olyszko's method of minorizations of discriminants, okay, maybe let me put an I here. So then in low degrees, and low degree here means I less than or equal to 22, each such irrep is a twist of 1 from a list of 11. Okay, so Tate twist means that the eigenvalues get multiplied by Q. So we have the trivial representation, and then its Tate twists. Those are the things that give rise to polynomial point counts. And then there are 5 that correspond to hospital modular forms for SL2Z. So here delta K corresponds to the weight K plus 1 cusp form for SL2Z. And then there's 4 that come from cusp forms for the symplectic group. So delta 19.7, delta 21.5, delta 21.9, and delta 21.13. And then finally, in weight 2, there's the symmetric square of the representation for delta 11. So this is a finite list, and you can stare at this, and so this gives a lot of conditional predictions. So you assume analytic continuation and functional equation, and then one of the things you see, so these first numbers, these are the weights, so those would be equal to K. So we get 1 in weight 0, and then it's in weights 2, 4, 6, 8, and so on. And then we have delta 11, and its Tate twists in 13, 15, 17, and so on. So in particular, there's nothing in odd weight less than 11. So then the prediction should be that on such an X, HI of XU should vanish for I in 1, 3, 5, 7, 9. And so we don't have a lot of spaces that are smooth and proper over the integer. The key ones are the moduli spaces of curves. So the Deligne-Mumford compactifications, moduli spaces of stable curves. And a lot is known about the cohomology of these moduli spaces. They're studied a lot in Witten theory, quantum algebra, algebraic geometry, enumerative geometry. And these predictions, so every prediction that you can write down here is consistent with everything that we know in the vast literature on the cohomology of moduli spaces of curves. So for instance, a quarter century ago, Arborello and Cornalba showed that HI MGN bar is 0 for I in 1, 3, 5. So this is for all G and N. So this is 1998. And okay, and maybe, yeah, so I feel like I made this transition too abruptly. So each of these representations gives contribution to point count, right? So, yeah, so if you had, say, a space that's smooth and proper over the integers, and let's say it has dimension 11, then you should have polynomial point count plus some non-negative integer times the point count contributed by delta 11. And what's the point count contributed by delta 11? Well, the point count over FQ is the qth coefficient of the cusp form of weight 12 for SL2Z. Okay, and there's a similar explanation for the contributions of each of these. So this theorem conditionally gives a very strong description for how point counts can behave for things smooth and proper over the integers, let's say of dimension less than or equal to 22. Oh, these? So these are cusp forms for SP4. And this is some indexing of Siegel modular forms. Yeah, so this is apparently a standard indexing in the literature, and I couldn't tell you offhand.
I think it's weight K1, K2, and so you just have this weight like 20 and 8 and
Okay. All right. All right. Thank you. Thanks. I think they're two dimensional. They might all be two-dimensional.
no, 4.
Oh, the 4. Okay. Sorry. Okay. So, all right. So now I should, maybe, close to.
There's no arithmetic proof. I mean, non-arithmetic proof that the HI is trivial for 7 and 9.
Well, that's what I was going to. Right. Okay, so this is joint work with Bergstrom and Faber from last year, which is that so HI MGN bar is 0 for I and 7 and 9. So we do have so that part. In subsequent joint work with Sam Kenning and Hannah Larson, we proved unconditionally all of the predictions here up to weight 15. And we also got some things that are not predicted. So we found that H11 MGN bar is for at least 2. So it doesn't vanish for G equals 1. So H11 M1N bar is non-vanishing if and only if N is at least 11. But then H13 MGN bar is a direct sum of Tate twists of delta 11. H2K MGN bar is a direct sum, so is pure Tate. So this is for k less than or equal to 7, so 2k less than or equal to 14. And H15 MGN bar is a direct sum of Tate twists of delta 11. And here again, you need G at least 2. So when G is equal to 1, you do get copies of delta 15 as well, but those don't propagate in higher genus. So they only live in genus 1. And so as a corollary, if you count points on MGN bar over FQ, so let's say G is at least 2, then you get some polynomial in Q, which is coming from pure Tate part, and then you get plus some int f of q, so f of q being the qth coefficient of the Ramanujan-Cusp form of weight 12, plus big O of q to the dimension. So on curves we had the expected part, which was q, and then the error term was of size proportional to square root q. So this was bounded by 2 root q. And so here, instead of having a 1/2 power savings, our error term is 15/2 power saving. So if you know the multiplicity of the Tate representation, the multiplication, the so this is polynomial, and so this A of q, this would be a polynomial in q. So that's the twists of delta 11. D is the dimension, so D is 3g minus 3 plus n. Yeah, good question. So we have a pretty good list now. So I think it's an open problem to give the complete list. Yeah, so I think now we know that M5 has polynomial point count. That follows from this. And then there's another argument, very beautiful, due to Sam Canning and Hannah Larson, that also shows that M6 has polynomial point count.
You're saying you don't even depend on the H13.
Yeah, because G is at least 2. Yeah, so yeah. Yeah, so in genus 1, we know everything. So I didn't write the genus 1 statement. So genus 1, there's an Eichler-Schmor correspondence that relates the cohomology of M1 n bar to local systems on the J line. And
Great, and arithmetic is more complicated than arbitrary. There's much more than delta.
no, because there's no level structure. I mean, if you go, but you have to go up to larger than 22 marked points. Yeah, here everything is less than or equal to 22. Yeah. And so once you, right, and so there's a reason why Chenevier and Landes stop at 22, which is that the L functions that are allowed are somehow related to sums over lattices, and there are special lattices that start in 23 and 20. And okay. No, n is unbounded. No, so but we have this, we have this big O. So, so if we know what's happening in low degrees, in low degrees we have low weights. Well, then by Poincare duality, that controls what happens in high degree, and so then we have, so this we have no control over, right? So this is going to have all the contributions from all the complicated modular forms, all the complicated motives. All we're saying is that there's a large power savings. Okay. Okay, so I guess I'm almost at the. Let's see. Is there anything more I should say? I had one more page of optional things. Okay. So yeah, maybe I'll say a couple words. Okay, so how does one prove such? And the induction works by excision of the boundary, or if you prefer, by applying Deline's weight spectral sequence. And so then you get terms corresponding to cohomology of open moduli spaces MGM. And there we have vanishing theorems that come from topology. So we have things like Harar's computation of the virtual. And so that will give vanishing certain terms in the weight spectral sequence. And then, of course, we use the Deligne-Grothendieck yoga of weights to show that the spectral sequence degenerates at E2. And so those are so that's the structure of how it works. And the essential difficulty, as is often the case with inductive arguments, is that as you increase the motivic I, you have more and more base cases that you have to treat. And then you have any method at all. And so in the work with Jonas Bergström and Karl Faber, we used point counting. And the base cases we needed was for G equals 4, n less than or equal to 3. And so then the Chenevier-Landes theorem predicts polynomial. And the reason is, so M43 has dimension 12, so you might worry about delta 11, but delta 11 we know contributes to H11 0 and H0 11. So any space that has delta 11 in its cohomology should have a holomorphic differential form, a holomorphic 11 form. But M43 we know is unirational, and unirational varieties don't have holomorphic forms. So there should be no delta 11, and therefore we should have polynomial point count. And what we did was we counted the points. And so it really was Bearhan's calculation. And so we got q to the 12 plus 4q to the 11 plus 7q10 minus 4q9 minus 13q8 plus 4q7 minus q6. Minus 11q cubed plus 2q squared plus 2q minus 1. And so this is done by stratifying the moduli space according to the Brillouin-Petrie type. And then so the interesting ones are the Brillouin-Petrie general curves, which are a complete intersection of a cubic and a smooth quadric. Smooth quadrics over finite fields come in two types, the split type and the non-split type. And we just go ahead and study linear series on, so the linear series of cubics on the split and non-split on the quadric cone. And then you consider all the possibilities for the singular locus, and you do inclusion exclusion. And then we discovered that the inclusion exclusion is very nicely captured by the Hasave zeta function. And so that enables a simplification of the computations. And so we got this, and we did the computation by Galois orbit count with all the denominators. We did it with Hasave zeta functions. And then for small fields, we did a complete census and explicitly listed the isomorphism classes of curves of genus 4 over F3 with their automorphism groups and rational points in order to count the number of isomorphism classes of 3-pointed genus 4 curves over 3. And since there are 1,497,092, which matches this polynomial and makes us pretty confident that in the end, these computations did come out right. Okay, so let me stop there.
Thank you very much for the very nice talk. And so questions?
Does this theorem predict or prove that if you have a smooth proper variety over Z of dimension less than 12 or something, then it will have polynomial point count?
Of dimension 10 or less,
10 or less.
or unirational and dimension 12 or less. Yeah, so that is the prediction, and that is, I think, absolutely an open problem. Right. Yeah. So we know it by moduli of curves, but for moduli of curves, we use an induction on G and N that is very special to moduli of curves. So I think, for instance, the classification of smooth projective or smooth and proper surfaces over the integers, I think, is completely open. So I think it's not known whether they are like uniruled.
So I didn't understand, but you said the prediction is for all varieties of dimension less than?
Yeah, so the prediction would be that if you have any, smooth, proper algebraic variety, but now it has to be smooth and proper over the integers. So that's a very strong. No, so elliptic curves, right? So this minus 16 times 4a cubed plus 27b squared, that's never equal to 1. And so there's always a prime of bad reduction. And so smooth and proper over the integers is an extremely restrictive condition, and that's why this is so rigid. And that's why, in some sense, the only large class of spaces we know how to apply it to would be moduli spaces of curves. But there's enough interest there that it's sort of worthwhile to give it a go. And but so classification of surfaces over the integers, I think, very interesting problem. There's a paper by Kare where he talks about this problem, and I think he has some partial results. Yeah.
So I kind of have a thank you. Similar in spirit question, because at the end, the calculation you described used one kind of miracle, well, semi-miracle, or at least sort of more exotic fact about unirationality to exclude delta 11. But then after that, it sounded like a very explicit calculation using how concrete genus 4 curves are. Yes. So let's say you go up to G, like M44 or M53, or like one step out, maybe delta 11 shows up. Is there any chance that you could still get some useful results if there's like exactly one extra Tate twist that appears, like maybe? I mean, so
delta 11 only shows up in genus 1. We do have L delta 11 showing up in all genera, and we know the L delta 11 isotypical part of the cohomology of MGN bar as a Galois cross SN representation. So that is maybe that's not in the paper that's on the archive, but we know that. So that part then becomes completely explicit. But also addressing your question, so if you go up to genus 5, we know that M5 bar has polynomial point count. We don't know the polynomial.
I see.
So so we know the count of the curve, so it's always q to the 2g minus 1. So I think that's in the old paper of Kissen and Lehrer, very young Mark Kissen. And so then there's the count of trigonal curves, and we know the count of trigonal curves, but that paper came out 2 years ago. And so then you're left with canonically embedded curves of genus 5. We know those are exactly the smooth complete intersections of 3 quadrics in P4. But now you have to count those complete intersections. And so you have points on the Grassmannian of 3 planes in the space of quadrics, but now you have to remove the ones that give rise to singular intersections and non-complete intersections. And yeah, I think at this point, no one has done that.
Just then, like, do you think that that's tractable? Like, is that likely to be doable if someone tries that, or is it intractable and there's going to be some horrible obstruction?
In between the two. I think someone will do it, and it will be hard work.
So you said MGN, of course, is a natural class of varieties with over Z. What about AGN? What's
Well, so the trouble with AG is so AG does have smooth proper compactifications over the integers, and but they don't fit into nice families with increasing G. So so there are nice modular compactifications of AG, like AG second Voronoi, which by work of Alexeyev is a moduli space of semi-abelic pairs. But the boundary strata are not. But those are not, sorry. And the boundary strata there have nice modular descriptions. So there you have the inductive structure, but it's not smooth. It's toroidal. And so you can make the smooth ones, but then they don't fit together into nice inductive families. So yes, one should study compactifications of AG using this method. But I think it's not so straightforward how to get the ball rolling. So I fully agree that yeah.
And aside from that, there are no other obvious classes that you could turn your.
That's my impression. Yeah.
And if you looked at something like varieties over Z of 1 over 11 or something, if you decided to invert a few primes,
then we have to ask Gaetan to do work. Yeah, could he please give us the list? Right. My impression is that that's not so obvious. And yeah.
When these guys proved this cohomology energy, were they motivated by this stuff, or
No. I mean, this came 20 years before. Yeah.
Or
no,
were they motivated by polynomial point count? Or?
No. Yeah. So the title of this paper is "Calculating Cohomology Groups of Moduli Spaces of Curves via Algebraic Geometry." So I mean, I don't want to, and this was really a seminal paper. So this is the paper where they give generators and relations for pic MGN bar. So they showed that H2 is equal to pic. They gave the generators, they gave the relations. And then this odd cohomology vanishing is maybe sort of a side note. And then they pose, then they make the observation that H11, M111 bar does not vanish. They pose the question about H7 and H9. So all of that is there. What was happening around this time was that people were making a lot of progress on cohomology of moduli spaces of curves by non-algebraic geometry methods. Right. So in some sense, part of the point of their paper was that algebraic geometry does have something to contribute to this topic, and really the main all arguments are driven by mixed Hodge theory. So they're driven by proper Leans weight. That's something that's not topological. It's really yeah. I think they were also interested in the tautological ring. So this was a time when people were really studying the tautological ring, and so they showed that H2 is tautological. They conjectured that H4 would be tautological, And then one of Arborello's students, Marcia Polito, wrote a thesis on that and proved that H4 is tautological for G at least 8. But yeah, so with Sam Canning and Hannah Larson, one of the things we did was we proved that H4 is tautological for all G and N, and we showed that H6 is tautological for G at least 10. And then, there's also a funny thing. So it turns out that tautological generation of homology is easier than tautological generation of cohomology. So another sort of theorem with Sam Canning and Hannah Larson is that H lower k is generated by tautological cycles. So for that, we got even k less than or equal to 14. And that was how we got the 7 here, 2k equal to 14. Right, so we were actually showing at the other end of the Poincare duality, we were actually showing that it's generated by tautological cycles, and therefore we know that it's pure Hodge-Tate. But yeah, okay, yeah. So yeah. So there are non-tautological algebraic cycles in H22 on M220 bar, and everything is built out of. So when Sim2 delta 11 shows up, it tends to show up with wedge 2 delta 11, which is Hodge-Tate. But because it came from wedge 2 delta 11 and not something tautological, it sort of remembers delta 11 in some sense. So this is coming, yeah, anyway, yeah. Right, so the M220 bar is because you have, so you have a boundary divisor, which is 2 genus 1 curves with 11 marked points on each. And so that's genus 2 with 20 marked points. So that divisor is contributing something. And so then there's some so you can find a cycle on M220 bar whose intersection with this boundary divisor is the diagonal. And so then, yeah, then you can use that to, yeah, so you study how the Kunath decomposition of tautological classes behaves. So you can make sense of the tautological ring on this boundary divisor, and if you had something tautological, then its restriction would have tautological Kunath components. And so yeah, so once you get an algebraic cycle whose that hits the diagonal, then you win.
If we have no more questions, let's thank Sam again for the meeting. And for the people here, we can go upstairs for the one